One. Hi everyone, my name is Paul Roysen. I'm a technical artist at SideFX. I am also the lead for the SideFX Labs initiative at SideFX. So in today's presentation, we're going to be looking at Python in Houdini. And this presentation is not supposed to be a follow-along type of workshop or training. It is really meant as a high to medium level overview of various things inside of Houdini that you can do with Python, and providing you with a couple of pointers and resources to look into those specific things that I'm mentioning. So at the end of this presentation, you should have an overview of the kind of things that you can do with Python in Houdini and have pointers to learn about those yourself. So let's dive right into it. To begin with, all right, so we have Houdini, and Houdini currently ships with two different versions of Python. The first one is Python 2, which is the one that has been a default for a very long time. But since the release of 18.5, we've also been shipping a technical preview for Python 3 of Houdini. The version of Python that we're going to be using throughout this presentation or training is going to be using Python 3, which is also going to be the default Python version for the next version of Houdini, which is Houdini 19. Python 2.7 will still be available as a build for the next version of Houdini, but Python 3 will be the default from then on forward, just like the VFX reference platform states. So how can you check which version of Python you're running in Houdini? Well, there's a couple of different ways. First of all, if you're using the launcher, it's going to say Python 3 behind it currently. On the download page itself, you can see that it's split in two. So you have daily builds Python and daily builds. Once again, starting with Houdini 19, the default one is going to be Python 3, and then this is going to say Python 2 as a sort of optional type of thing. Additionally, at the top of the bar for Houdini, it's going to say Python 3 currently. But the other way of checking it, in case you have this disabled or you have it hidden or you're full screen or something else like that, is by simply going to the Windows submenu in Houdini and then clicking on Python shell, which you can also access with the hotkey Alt-Shift+P. Then once you click that, it's going to open up a Python shell, and that is going to mention the exact version of Python that you're using. So as you can see here, it is Python 3, and to be more specific, it is Python 3.7.4. All right, so next up, writing Python in Houdini. So there are a couple of different ways. Let's say you're using a Python SOP, and you want to modify some text. What you could do is you could select your text. You could hit Control-C, open up your text editor, hit Control-V, modify your code there, and then copy it back into Houdini, like you see here. And this is a bad way of doing it, because now essentially you're going to have code in two places. You're going to have code inside of Houdini, and you're going to have code inside of an editor, and you don't know which one is the most up-to-date version. Especially if you're using, multiple Python SOPs, or you have multiple places where you're typing scripts, it's going to get confusing really fast, and it's just error prone in general, because sometimes it doesn't copy correctly, or you didn't paste it correctly. So this is a bad way of working. So let's take a look at a better way of working. All right, so you can right-click on the label that says Python code on the Python SOP, and then just edit string on it, which is going to open up this editor, which brings up something that's a little bit more representative of an editor inside of Houdini. But this is also not yet ideal. So even though you have more screen state here to edit text in, and it's going to paste it into the actual string field once you're done, it is not ideal yet. So let me show you something that is the best way of working, which is something that we ship with SideFX Labs, and that is using the external editor. So once again, you click on expression, but in this case, you type edit in external editor. And what that's going to do is it's going to open up that editor that you've selected, which it will prompt you to set the very first time you open it. And then it's going to open up the script in there. You can just modify it. And then once you hit save, by hitting either file and then save or Control-S, it's going to automatically update that script inside of Houdini as well. And as you can see, it actually stores a temporary file on disk that refers to that Python SOP or a wrangle or a shelf tool or anything else that stores code, and that's where it's going to store that code. Right now, in the example in this video, I am using Sublime Text. That's just my preferred editor, but you can set this to be any text editor that you like. For example, Visual Studio, Notepad, WordPad, Microsoft Word, whatever it is you want to edit text in. I wouldn't recommend Microsoft Word, but if that's what you want to do, then that's what you want to do. So how do you set that? First of all, you go to the Edit menu that you see here. You then go to Preferences, and then all the way at the bottom, you can say Set External Text Editor. Additionally, like you saw in the previous video, you can also just right-click on a parameter and say Edit Expression, and then Edit in External Editor. And if that's the very first time that you use that, it's also going to pop up this window here. So it doesn't really matter how you access it, it's going to access it the same way. Next up, you can go to the executable location where your editor is located. So in this case, for me, it is Sublime. And then you just click Open, and then you're good. You're all set for writing Python inside of your external editor. All right, so now we've seen that. Now we've seen the version of Python. We've seen how to set an external editor. So let's take a look at something a little bit more practical. In this case, let's take a look at PDG and work item generation using Python. So in the example that I'm going to be using, this node from Labs called Generate from Image Planes. And the purpose of this tool is to basically load up an image from disk and then make a work item for every single image plane. So let's say you're loading a JPEG. A JPEG only has a color channel. So in this case, it would generate one work item, which means one work item for the color channel. If you were to load, say, a PNG with an alpha channel, it would generate two work items, one for the color channel and one for the opacity channel called alpha. So how does it work? You use, let's say, a file pattern where you load up your images from disk so that now you have a reference to it, right? In this case, you have this PNG here. It has an extension and a file name, and then we plugged it into the generate from image planes. And what's that going to do? It's going to generate two work items, like I said before in my example, because it is a PNG. We have one work item with the image plane being set to C, and we have one work item with the image plane being set to A. So what is it? We use an input image, and that gets converted into a work item per channel and an attribute describing the channel. And the reason I'm showing you this tool is not because I'd like to promote this tool, but because it is a good use case of using Python in PDG to generate work items. So let's see, what does it look like? This is the node on the top surface level. Inside of it, you have the Python processor, which is doing all of the work. Additionally, we also have a copnet, and the only thing that is found inside of the copnet is this file cop, and that's just going to load up the image so that we can do some processing with it. All right, so let's take a look at the script for that node. This is everything that is contained inside of it. We're going to be breaking it down in just a little bit on the next slide, but I just wanted to show you this window here. When you're working in PDG and you're editing a string, or let's say Python, you get this really convenient window pop-up, which has all of these built-in expression variables that you often use. So it's sort of like a easy way to look up those things in Python so that you know what you have access to. All right, so let's take a quick look at the code itself. It consists out of three main elements. So let's take a look at each one of those. First of all, at the top, you saw that we have this default comment that PDG provides you in the Python nodes. It also explains what a couple of built-in predefined variables are from tops. First of all, you have self, which is a reference to the current pdg.node instance, right? So what is the node that we're currently processing? Item_holder is, as you can see here, a pdg.workitem holder for constructing and adding work items. So this is an important one for us because we want to add work items. Next up, we have upstream items, which is the list of work items in the node above, or an empty list if there are no inputs. This one is also important for us because, like I said before, with this node, we essentially want to load in an image and process it and generate work items based on it. And then next up, we have generation type, which is just the type of generation, for example, static, dynamic, or regenerate, which essentially just describes what the type of action is that the node is currently doing. All right, so let's take a look at the code itself. What we have here is a cook node at the top. we have make work items, and then we have just this script here. So at the top, we were just defining some functions. This is not going to run, it's just going to compile it and know that we have access to these functions later on. These lines here are not part of a function, so it's going to run these immediately because, as you can see, it's not indented or anything, so it's just going to run as soon as it hits that. So what is this doing? Let's take a look at the next slide. All right, so if the length of the upstream work items is larger than 0, which means that we have upstream work items, what we're going to be doing is we're going to loop over every single upstream item inside of all of the upstream items, which, as you saw before, is the list of work items in the node above, or empty list if there are no inputs. So this gives us all of the work items to loop through. And then what we're going to do is we're just going to call that function we saw earlier called make work items for that current work item. And if it is not larger than 0, it's just going to call work items as well without an argument, which we'll see later on what that does. All right, so make work items. What is that doing? First of all, I'm going to point you to 2 resources. We have this docs page for work item holder and for work item, right? So that's these 2 things that we saw here above. The work item holder, which is the container essentially for constructing and adding work items, and then the work item itself, which has a lot of information inside of it that we're going to be using to add attributes, to read attributes, or to modify attributes. So let's see, what is it doing first? We create a variable called image planes, and that's going to be getting a value that comes out of self.scheduler.run on main thread, which is going to do something in a function called cookNode on the main thread. So this is a really convenient function that not a lot of people know about because it's fairly new, which allows you to actually cook the Python of your script on the current main thread. So this would essentially be the same as cooking something in SOPs, where everything happens on the main thread. It will not spin up an instance, a Python instance in the background and cook everything there. It's actually going to cook it on the main thread, which means it's going to block your Houdini session. And the reason I'm doing that in this case, and the reason why I'm paying attention to this, is because it is required when you're dealing with cops and you want to evaluate files. So in this case, what it is going to do in this cook node, which we're going to look at in a little bit, is it's going to evaluate the image planes from that file cop that we saw earlier on. So now that we have these image planes, which is going to return us a list of, let's say, C and A, we're going to loop over it. We're going to get an ID and the image plane out of that list that we created earlier on. And so depending on whether or not we had a checkbox turned on the node called inherit upstream work items, we're going to be adding a new work item with the parent set to the previous work item. So that means that on the image that we saw earlier on, where we have one work item being split in 2, these work items are going to inherit all of the properties of the work item they inherit from. If not, we're just going to be creating a new work item that is not inherited from anything. So if you were to inherit the upstream work item, you're of course going to inherit that dependency. If you do not, there will be no dependency between those. So that's an important distinction to make there. Once we have that work item created, which is called new_item, we're going to be adding an attribute to that work item called attribute name, which is that parameter that we defined earlier on. And so this is the way to create and set a attribute value on a work item with a variable. All right, now we've looked at PDG. Let's look at a different type of thing to do with Python. Let's say we want to run and execute and communicate with third-party applications. A useful node to take a look at inside of SideFX Labs is the Instant Meshes SOP. The Instant Meshes SOP, like it says, is running the Instant Meshes executable. Instant Meshes is a Quadra mesher that is open source and completely free, which you can find on GitHub, that we've simply taken and integrated into Houdini through SideFX Labs. So what does this node do? As you can see, you can set the poly count, you can set a couple of arguments or parameters called in Houdini, and a path to the executable that we want to run. Inside of the node, we can see that we have these subnodes. We have an input, we have a cache input, so that we have some caching happening in the geometry itself. We have a file node set to write and not read, so it's going to write this obj every single time it cooks. And it's going to do that, of course, only when this cache is dirty. So this is a way to prevent it from cooking every single time, even if there are no changes upstream. Next up, we have that Python node, which is going to execute some things. It's going to also write and read geometry. And then we cache the output again to once again make sure that we only really recook this part of the network if there are any changes upstream. And then we just add some normals and then we output it. So let's take a look at the Python SOP that we saw, right? So this guy here. We can see that this is the entire script that we have here, right? So this part here and then this part here. So what are we doing? First of all, we're importing some modules or libraries, the most important one being Subprocess. Subprocess is a module that, like you can see here, allows you to spawn new processes and connect their input-output error pipes and obtain their return codes. So what it does is it allows you to run executables, run commands, communicate with those, kill those executables through Python, which is super convenient because now we're essentially able to run an executable from within Houdini through Python. So what do we do and what do we need to worry about when we are running third-party executables? Well, in Houdini, we're often dealing with parameters to describe how we want to do something. So important for us is that we take those inputs from the user, right? These parameter values here, and feed those to our executable. So what we do is we just define some variables here, and then we just evaluate the parameters that we care about so that now we have the values. So for instant meshes, this would just essentially be evaluating this parameter here, giving us the path to the executable. The number of polys, which is going to evaluate the parameter called poly count, is just going to evaluate the parameter that gives us the poly count. And so on and so on and so on. We can also define an error, which in this case is just a line of string. And then we can raise that error if, for example, the instant meshes executable is not found. So that is a really easy and convenient way of getting that error badge that we see here if, for example, the user did not provide the correct information or parameters or anything else that hasn't been properly configured. So we have raise who.node error, which is going to give us an error. We can also do raise who.node warning, which is going to raise a warning. And we can also do raise who.node message, which is just going to give the user a message. The difference between those is that the message is, like it says, just a message. The warning is going to give a warning, but it is still going to continue executing the script. And the node error is going to error out right here and is not going to continue cooking the node. Next up, what we need to do for Subprocess is essentially build a command string. And the way I like doing that is by creating a list where I just initialize a list with that path to the executable that we're going to be running. And then we just append all of the different arguments that our node needs or that the executable needs. So in this case, we have the deterministic, quad dominant, the crease angle, right, which is just the dash C and then the actual value itself. So now we're essentially getting a list of all these different arguments in sequence that we're going to pass on to Subprocess and the executable that we're going to be running. And that allows that executable to evaluate those correct arguments and use those to process the data correctly. So once we have that list, we can see that we get this this part of the code here. And what this is it's essentially just specific to Windows because it says here os.name is NT, which means Windows. All that this that really does is it just hides the pop-up window that shows up when you execute some executable. So the most important part of the script is this here, which is going to bring up and run that actual executable. And that's what we do using subprocess.call. As you can see, this is the first real part where we're using subprocess with the important part. We're also feeding it that startup info, which is going to hide that dialog on Windows. And what this is going to do, this line here, is it's going to feed those lists of arguments that we constructed earlier on to the executable and actually run it, right? So what Instant Meshes in this case is going to do is it's going to load in a file, that .obj that you saw earlier that is being saved to disk. It is going to do the quadri meshing in the external application, and then it's going to write that to disk as, let's say, another obj or an FBX. And then once that is done, it skips on to the next line, which does geo.load from file. And geo.load from file does exactly what it says. It just loads geometry from file. And so what we're resulting with now in this Python node is we have our Houdini geometry, right, that we saw here, which is our original pig head. And then as soon as we reach this Python node, the only thing that this Python node is going to return is that newly remeshed quad geometry. So that's what that load from file is doing for us. For more information on Subprocess, I recommend this link here, which just gives you this Subprocess module, which shows you all the different methods and information about the library. All right, so that was executing geometry or Python in network, right? We run Python from within the network. Sometimes, however, you want to do something a little bit different. You want to run some Python code based on user interface events, right? So we have this button here that says convert and export on the skinning converter node. So we only want to run some sort of Python code as soon as you click that button. We do not want to run the Python code as soon as this node cooks, right? Which is what would happen if you set this display flag, which is different from the Instant Meshes node, because that one is going to cook as soon as you actually click on the node itself. So how do you set something like this up? Well, we've seen the previous one, and this one is a little bit different. This one is going to be using something called parameter callbacks. And what that allows us to do is it allows us to attach a callback to a button that is going to run some Python somewhere based on those values. So you can see inside of this node, there is no Python sub here. So all the Python code gets run from within something called the Python module. So what is a Python module? Python module is just a piece of script that is stored inside of an HDA, right? So inside of this Dembone skinning converter HDA as something you can access from anywhere. So that allows us to, for example, define functions inside of here and run those functions from anywhere, from the interface of this node, from another node, from the shelf, or from anywhere else that you want to run that code from. So in this case, what this script here is doing is it basically just executing some code that is going to save an FBX from disk. It is going to once again run Subprocess to run, in this case, Dembone skinning converter. And then once that's done, it is just going to export that as an FBX to disk. And then that's what this node does. For more information on the asset modules, which is extremely powerful, I recommend this documentation page, which is inside of home, and then locations, and then asset modules. If you want to see more ways of running Python code in HDAs, here's a couple of examples of nodes that I recommend looking at. We have the Instant Meshes that we looked at, which is the in-network processing of geometry. We have Labs Alice Vision, which is similar to that, but it's running command line scripts for about 11 apps all at once to do some photogrammetry processing. We have Dembones, which is, like we saw before, an interactive way of running Python code using callback scripts. And then we have the Gaia Tor processor, which is bidirectional in and output with third party. So this node is a terrain tool that is running something called Quad Spinners Gaia, which is another terrain application. It saves out a height field from Houdini, loads up Gaia, has Gaia process the height field, and then save out those masks from Gaia, load those back into Houdini, and show that as an output to the user. So I know that we ran through the examples that we saw before fairly quickly, but that is why I wanted to point out these tools so that you can look at them by yourself. So ones that we covered are Instant Meshes and Dembones. So if you want to look at the Python script in more depth, that's the tools that you should take a look at. All right, so now that we've run tools, let's look at something else. Let's say we want to create shelf scripts. To create shelf scripts, what you could do is you could just select your nodes and then drag and drop those onto the shelf toolbar, and that is going to generate Python script that you can simply execute or modify. So very easy way of creating Python script. So let's take a look at that again. Just drag and drop it. It's going to create that pop-up window that allows you to create shelf tools. And then when we look at the code, you can see that we have Python code describing the creation and placement of those nodes. So you might say, job is done. We can just run that and use that. But I'd like to go a little bit further because the code that we just saw is extremely messy and complicated because it is automatically generated Python code. So how would we do this ourselves manually using Python? Well, I'm going to be showing you step by step. First of all, what we need to do is just right click on the shelf and just hit new tool. And that is going to pop up an editor. And then inside of the editor, we want to, first of all, create a geometry node or use an already existing geometry node. In this case, I'm going to be using an already existing node. And then we want to generate or create a node. So the way we do that is, first of all, import who, which is hom, right, or Houdini Python. We have a reference to the node itself that we're going to be creating something in. So this is the parent. And if you don't want to type this by hand, what you can do is you can just drag and drop this node into the text editor, and it's going to create this line for you. Next step, what we want to do is we want to create a node, and that is very, very simple in Houdini. You just say parent node dot create node, and then you want to use the internal name of the node that you want to be creating. So to get this name, just middle mouse click and hold on a node, and it's going to show you right here. Some nodes have version numbers behind them, some have another namespace. You need to include that entire thing that you can find here between the round brackets. For more information on subnodes itself and what you can do with them, this is the documentation to look at. So now that we have this one line of code, once we click that, you can see it is going to find the parent node, which is that grid node that we saw, and it's going to create a node called Platonic. Wow, very easy, very convenient. We now have a shelf tool that is going to create a node with just a single line of Python. Super powerful, but this isn't quite useful for us yet. So let's take it a little bit further. As you saw in our example, we want to be creating 3 nodes, right? We want to create a Platonic solid, we want to create a polyextrude, and we want to create a polybevel. So what we do is we just repeat what we did before, but in this case I swapped it a little bit around. We now have a variable called parent node, which is just a reference to that grid node that we saw before, the parent, right, called parent node. And then we're going to be creating 3 new nodes. We're going to be creating the Platonic solid that we saw before. We're going to be creating a polyextrude called polyextrude semicolon 2.0. Polybevel, once again, exact same thing using the internal name, which is going to give us these 3 nodes. Next up, we need to create the wires between them, because otherwise Houdini is not going to know that these have to do something together. So how do we do that? Well, very easy. We're just going to use the variable that contains the node that we want, and we're going to call .setNextInput. And what that's going to do is it's going to set the next available input. In this case, because we don't have any inputs yet, it's just going to set the first input. As you can see, the polyextrude node is going to set the next available input to the Platonic solid. So it's going to create from this node a line that goes from here to there. Easy. Now we have these 2 lines here. Next up, we're going to be connecting the polybevel node. So polybevel.setNextInput, polyextrude. Well, voila. What we now have is Platonic solid connected to the polyextrude, which is connected to the polybevel. And that's going to give us this. Not quite that soccer ball that we saw before. The reason it is not the same yet is because, of course, we haven't touched any of the parameters yet. All right, so parameters. How do we set those? First of all, select your node that you want to be setting a parameter of. Hover over the parameter that you want to be setting. And then that's going to give you this tooltip, which is going to show you here the internal name of the parameter. And so what we need to do then is we just say the node.parm. And then between brackets and as a string, we're just going to type that parameter name. So in this case, type, and then just say .set, and then the value you want to set it to. So in this case, 5, which means the soccer ball setup. And we're going to do the exact same thing for the polyextrude node. We set the distance of the extrusion. We want to set the split type to elements, and we want to set the offset parm of the polybevel to a specific value. So now when we run it, we're going to see we have that soccer ball, but the nodes are all sort of overlapping on each other, which is not quite what we wanted. We want it to be nicely oriented like that. You also notice that the display flag is not correctly set. We only see that Platonic solid and we don't have it set on the poly bevel. So you might say, well, I just click on the display flag and it's all good. Well, if you're dealing with Python and using Python to create, modify, and set nodes, you need to do all of these manual interaction steps that you're usually doing in Network Editor through Python. You can do literally anything that you want to do with it. At the end of this talk, we're going to see a really cool example showing it at the next level, but that's for later. So how do we set the display flag or the render flag or any other type of flag that we want to set? Well, that's really easy. You just call the node, right? Polybevel dot set display flag true, which is going to set the display flag, and then polybevel dot set render flag true. If you want to set the render flag to be something else, for example, something that subdivides, so you have high poly, you can do that too. But this is just showing you how you can set the node flags through Python. Additionally, we just skipped over these two lines, which is going to lay out our nodes nicely. So in Houdini, what you can do is you have the ability to organize your node network, right? As you can see here, I'm just selecting them, holding A, and then dragging down, which is going to do a layout. We can do that exact same thing in Python on a per node basis. To do that, all we really need to do is say polyextrude.move to good position, which does exactly what it says. It's going to move the node to a good position. And we're going to do that one by one from the node tree downwards. So it's going to do, first of all, move the polyextrude. So it's going to get the polyextrude from here, move it down. Voila, perfect. And then it's going to take the polybevel, which would also be here, and then voila, move it down there because it knows that the polyextrude is now there. And so now when we click it, we have our awesome soccer ball all created through Python as a shelf tool in a total of, let's say, 20 lines of code total, right? And then if we remove all the white space, it's going to be even less. This is all readable code. We can add comments, we can add our own notations to this code. It's super clean and easy to maintain, which is a lot better than the drag and drop easy solution that we saw before. So once again, we can see that example. And what that gives us is just regular good old Houdini nodes that we can go and select. We can modify the parameters, do anything else with it, all created through Python. So it's super powerful. I know that it's an extremely simple example, but imagine if you spend more time than the few minutes that we spent on this to create your own things in shelf tools through Python. Next up, some processing in Python. So we've now seen various things. We've seen executing external applications. We've seen creating shelf tools. We've seen creating work items. So what else can you do with Python in Houdini? Well, a lot. So first of all, let's talk about processing node networks. So let's say you're a TD at some company, and you want to figure out what nodes are our users using the most. Well, what you could do is you could hire 50 people from the street and tell them, please load up Houdini and count every single node that you see and tell me exactly how many of each type of node that we have in our network. Why would you do that? Well, if a particular type of node that you've created yourself is being used the most inside of your studio, you probably want to make sure that that tool works at all times and has the highest priority in terms of fixing it, updates, or even creating performance optimizations. So it's really useful to know how often a node is used. And so that's really easy to do inside of Houdini. All we just really do is once again do that parent node equals and then the parent node of our network, so in this case that geometry node called example, and then we just get all the nodes by saying parent node.children, and that's going to give us this giant list containing every single node inside of our parent node. We print that and we get that, so we could be counting these instead. That makes it a little bit easier already. But if you use the counter object from the collections library, what we can do is we can just tell it to create this counter object for all of our nodes. So to do that, we're going to do some basic list comprehension, where we're just getting the node, right, x, which is basically for loop in here, where we're looping over every node in all nodes, where we're getting the type of the node and then the name of the node. And that's going to get us that internal name that we used earlier on to create nodes. So now we have a list with not this who.sub node of type labs mesh tiler at and then the location, but instead what we're going to be getting is just the internal name, so labs mesh Tyler, right, which is the part that we're interested in. We just run that with the counter object and print it, and that's going to tell us we have 7 attribute wrangles, we have 4 copy SOPs, we have 2 time shifts, we have 1 assemble, 1 grid, and 1 of all these other nodes. So very easily we could see that we have a network that is very heavy in terms of attribute wrangles and does a bunch of other stuff. So this is super useful to process your own HIP files that you have at your studio and figure out what is it that people are doing. You know, is everyone writing vex? Is everyone just using nodes? Which nodes do we need to pay most attention to? Well, this allows you to do that. And a lot more, of course, because it's just a simple example. All right, so now that we have processing a node network and checking out what type of nodes people are using, let's look at a more practical example. All right, so let's say we have this node from labs called Maps Baker. And as you can see, the Maps Baker has 4 different versions. These are all different definitions. And as you can see, currently, the node that we have in our network is not set to the latest version. We have version number 3 instead of version number 4. So let's say we have a node in your studio called Cool Explosion Maker, and it has 3 versions. Versions 1, version 2, and version 3. Version 2 is the one that was, released last month. And then we have a TD that did some optimizations, some bug fixes, and they now release version 3. Well, all of the networks that we're using Explosion Maker number 2 are not going to be automatically updated to the next version as soon as we release it, because Houdini tries to ensure backwards and forward compatibility with node definitions. So it's not going to switch it, it's just going to say, well, I'm using an older version, but it doesn't show you in the network that you are using an older version here. So how do we do that? Are we going to select every single node and check if there is a newer version? No, because we now know Python. We know that we can do things a lot smarter. So what we can do inside of the assets menu here is take a look at the example from labs called check assets versions in scene. And what that does is it just looks at all of the labs nodes inside of our network, and it's not going to upgrade them automatically because that could potentially be dangerous. It's just going to tell you, warning, node instance is using older definition, and then the location of the node itself. So now we can, write this out to a text file, email it to someone and say, hey, your file is using an older version. Please take a look at them and update them where possible. So how do you create scripts that get run from within a network or a drop-down menu like this? Well, another practical example. We're going to be using this version checker. So first of all, how do you create those menu items without even running any script? Well, Houdini has this really cool thing called mainMenuCommon.xml. Every single UI element in Houdini that is a menu or something that has some sort of menu with sub items that you can click on, like the right click menu, like this menu button, like the parameter interface, has an XML file that describes how it is constructed and what items are inside of it. So in SideFX Labs, we ship this file called mainMenuCommon that is Houdini is going to load in and overlay on top of the mainMenuCommon that Houdini has itself. And what that allows us to do is allows us to describe which menu we want to put something in. So in this case, the assets menu. And we're going to be creating a script item, which just means we want to create some sort of item inside of our menu here that is just, as soon as you click it, going to run some script. Python in this case, right? Because our talk is all about Python. We then have a label, which allows us to describe what it is that we want to show in the label. We can say where we want to insert it in the list. Do we want it to be at the top? Do we want it to be at the bottom? Well, I'm just using an index number 10, so it can put it there. And then the script that gets run as soon as we run it. So in this case, we have this bracket here pointing to the left, exclamation mark, C data, a bunch of Python script, and then we close it here. So these parts here are just something that Houdini needs to know that, whatever is in between it is a Python script. It should not be processed any different way in this XML, and then the Python script itself. So let's take a look at the Python script and see how we did it. All right. So we're going to be using some information from something called the node type of a node. So before we saw that we were using who.node, and then that gives us a node object. that node object has a type, right? We want to know what type is this node. Is it a box? Is it a sphere? Is it a map spacer? Is it something else? This gives us access to that information. All right, so first of all, let's grab all of the labs nodes that we find in our network. So how do we do that? Well, we're doing some other list comprehension where we're just getting the who.node and then this / which just means Houdini root, all subchildren. So this is going to give us every single node inside of our HIP file. And then we're going to be looping over every single node that we find in this subchildren list. And then we're going to only add it to this list if that node type, right, the node type, has a name component where the second index is called labs. And that is important because we only want to have labs nodes. So if you work at Studio X, then the name component could, for example, be X, and then you only get the nodes that have a name component of labs. So what is that giving us? Well, as we saw before, in this case, the mesh tiler is part of the labs namespace. So it is going to be getting this node, but not, for example, the color sub, which is important because we don't really care about color sub. We're only really interested in nodes of our own studio. Once we have that, we're going to be looping over every single node that we've found. And then we're just going to get the node definition of that node. So now we have access to the definition of, let's say, the map spacer. Then we're going to get the name of the node types. That is going to give us that lowercase string that we saw earlier on. This one here, labs mesh tiler. And if that is not equal to the node type, the node type with the namespace order with the first index, which is essentially going to return us the preferred version of the node. So in this case, it would give us mapspacer 4, whereas this would be mapspacer 3. It is going to say these are not equal, and therefore we need to print the node instance is using an older definition and then the node path. So this is a little bit complicated, and I don't want to spend too much time on explaining this because we have a lot of other stuff to cover. But take a look at this page here, and you'll find that this will all make sense very quickly once you get to work on it yourself. All right, so next up, what else can we do in Python in Houdini? Something that a lot of studios do is run something called startup scripts. And startup scripts allow you to run a Python script as soon as either Houdini opens or as soon as we load a HIP file. So let's say you're a company that does a lot of rendering and you have this preset file that your artist should be using, right? We have some lights and we have a ground plane, and every single time they open Houdini, we want them to automatically load this file. Well, what we could do is we could either tell them, please load up this example file that we ship and we have on our network, and then use that as a starting point. But as we all know, people are going to forget about it. So what we want to do is we just want to boot up and initialize the Houdini scene with this as soon as they open Houdini, so that they don't even have to pay attention to it. So how do we do that? Well, Houdini has a couple of different Python scripts that can be placed in a very specific location where Houdini knows about them. And the two most important ones and commonly used ones are 123.py and 456.py. And with some thinking, 123 is essentially starting up Houdini, right? 1, 2, 3, steps 1, 2, 3. And step 456, which is after Houdini is booted up, is going to run as soon as the file is loaded. So 1, 2, 3 runs as soon as Houdini is started without the scene, right? So if we start up Houdini from, let's say, the launcher, or we just double click on the executable, it is going to run this script. But if you already have Houdini open and we do file new, it's going to run this script. So for our purposes with the startup script, what we're going to be doing is using that 123.py because we want to open that file as soon as they boot up Houdini. And so all we really do is we just do that exact same thing that we did before with the shelf tool, where we create a root object, or refer back to a root object, my apologies. We then create a grid, right, the ground plane, by using this, like we saw before. We then create two light objects. We're going to be setting the parameter values on all of the light objects. And then we're going to do some scene organization. So Houdini can do way more than just creating nodes and setting parameters. It can also, for example, create network boxes. It can move nodes. It can set comments on nodes. It can set display flags. So all of that, gets done here in Python as well, giving us that file that you saw here as soon as you boot up Houdini. Display flags set nicely. We have them in this network box. The network box has a comment in there. We could do whatever else we want to do. We can change the node color. We can change the wiring. We can do whatever else we want to do in there. All right, so the latest addition to what can we do in Houdini with Python is something really cool, and that is Python states. And Python states allow you to add another layer of interactivity on top of Houdini nodes that already exist. So in this case, the 3 examples that I have are all labs nodes. We have this decal placer, which allows you to essentially just move your mouse over a piece of geometry and use the scroll wheel to change between pieces of textures that you want to place. We can use shift to increase or decrease the size. We can rotate them. And that's all done through Python states using nodes that we're simply setting parameter values on. So this example here is called the pick and place tool, also in labs. And that's just a very simple tool that allows us to click and drag anywhere in the scene to place objects and rotate them and scale them based on the mouse position. Once again, it's just a simple node with parameters, and all Python states is doing is it's modifying these parameters based on what it is you're doing in the viewport. If you script that clicking and dragging modifies a certain parameter, then that's what it's going to do. It's just going to modify that parameter as soon as you click and drag. We can take it as far as making it a complete UV tool, right? That allows us to UV objects with, let's say, an overlay on the screen like this, where we can select a piece of texture by clicking on it here and just assigning it anywhere on the geometry using Python states. So what else can we do with Python states? We can display handles. So if you want to, for example, show or move a transform handle, you can do that. You can create your own handles, right? If you want to create your own rotation handle that looks a very specific way, you could do that. You can interact with geometry, for example, by drawing on them, if displaying information about what's under the mouse cursor, for example, printing what the color of the primitive is that you're selecting, or printing the material name that is under your mouse cursor. You can display guide geometry. So we can do what we saw here in this video here, which is rendering additional geometry as, for example, a highlight in the viewport. We can respond to user interactions with state parameters. So if, let's say, you want to have a really tight connection between doing something in the viewport that modifies the parameters, but also the other way around, which is doing something in the parameter interface and doing something in the interface, for example, changing some sort of text that you're rendering in a viewport, you can do that. You can do selections. You could display custom right-click menus, which is something that pick and place tool was showing. We can do low-level mouse, keyboard, and tablet events. So for example, get the difference in movement for the mouse. Is the mouse moving left, right, up, or down? Are they clicking on the mouse? Which buttons are they clicking? Left button, middle mouse button, right button, the back button, anything else? You could do tablet events if you're using a pen. We can wrap things in undo blocks because that is what users expect. And we can run across multiple context levels. For example, OBJ, SOPs, and LOPs. So creating a Python state might sound scary, but it really isn't. All it really is a Python script that you find under the interactive and then viewer state tab of your node. So how do you find all the different Python states as examples in Houdini? You just click on the plus here. You go to new pane type, inspectors, viewer state browser, and that is going to show you this entire list of all the different Python states that Houdini ships with, and all of the Python states that you've created yourself already, including nodeless states and states for Node itself. So if you're modifying a Python state or you're looking for a specific something, that allows you to find them very easily. So creating a Python state, I'm going to show you how to do exactly that. First of all, create some sort of HDA. Then go and create some parameters that we want to modify using our Python state. Go to the interactive and then viewer state menu in the type properties of your HDA. Click this new button that you see here. And that is going to pop up this really convenient window that allows you to create some pre-configured Python state where we can set the name, label, description, icon, and also create all of these events that Python state knows about. For example, mouse event, mouse wheel event, key event, drag and drop, on draw, handle to state, exit, enter, interrupt, generate, all of the different stuff that Python state uses. So our easy example, we just want to modify some parameter whenever we scroll the scroll wheel. So what we could do is we could just use that on mouse wheel event, which we can find here. So if you tick that box, it's going to create this piece of script here for us. And then all we really do is we use this already predefined code. We find the node that we're currently dealing with, which is our HDA. We're going to get a reference to a parameter, in this case, the calls parameter for the tube that we saw here, that we have, right? Number of columns. And then we're going to set the value to whatever that parameter is already set to, right? Because let's say if it was set to 5 and we scroll up, we want it to be 6. So in this case, we take the value it already is on, and then we just add the scroll value, which is something that was pre-generated, to that, and that's going to give us that parameter value with now an incremented value. So now we've created our very first Python state ourselves. That is just a simple tube that modifies the number of columns based on the scroll wheel. Next up, so now we've seen a lot of Python in Houdini. Let's see how far we can take it. Well, there was this cool video that I saw online from Stefan Welsh, where he essentially was a little bit frustrated with users always clicking the template flag if the display flag is set to on as well, which I am guilty of. And we just have a little kitty that turns off that flag as soon as you click it. Well, I wanted to see if I could actually implement that in Houdini instead of it just being a pre-rendered video. And the answer is yes, I was able to do that, and that is what you're seeing here. What I'm doing essentially is I'm making use of the network editor image functionality that Houdini has, which allows you to place images in your network. And I'm using, a flipbook to essentially animate it or make it appear as if it is animated. So I have every single frame of that video that we want to play, and I'm just going to create the network image and just swap that image to the next frame at a certain interval. Once again, shout out to Stefan for giving me all of these files and rendering out for me so that I could use these. The functionality of creating network editor images is also something that we've made easier with SideFX Labs using the sticker picker, which you can access by clicking the Labs menu here in the network editor, and that allows you to place images. So let's take a look at the actual script itself very briefly. All of this is also covered on a tutorial that you can simply find online on 80 level by typing in on Google kitty template flag callbacks. But I just wanted to quickly show how I did it. So once again, we have our node object. We add an event callback. So this is basically saying as soon as this very specific event happens, run a piece of Python code. To find the documentation on that, visit this link here. We added the flag watcher, which means that as soon as the flag any flag on the node has changed, run a function called flag changed, which in this case, for our example, means as soon as we click a template flag, we want to check if both the display flag and the template flag are set, run some sort of Python code. So that's what we see here. Next up, we want to find the actual pane tab of the network editor that is open. If we don't have a network editor, we just want to close it because there is no network editor to edit, and otherwise just use the network editor. Next up, the most important part of it is the flipbook image. So what we do is we create a network image, and then we have this for loop that is just going to for loop over all of our frames that we created, right? So on that network image that we saw, we want to set the path to the next frame. We want to figure out what the bounds are of the network editor. So we're going to be, placing it at the exact location of the node because they have to be on the node. Otherwise, the kitty is going to just hit somewhere in the middle of nowhere. We want to resize it so that it fits with the node. And then we're going to say, network editor, I've configured my image. Please add it to the network editor. And then we're going to be setting the template flag to false, right? Because the kitty has to turn it off at a specific frame. We then are going to tell the network editor to please redraw, right? Because the network editor now has a node with display flag turned off. And then we're just going to sleep for the frame rate, right? So in this case, 1 divided by the frame rate of, I think it was 20 frames per second. And so this for loop is basically just going to do change the frame, sleep a little bit, change the frame, sleep a little bit, change the frame, sleep a little bit. And this would, of course, hang up your network editor because, this sleeping would block the main thread. But I have a little bit of a trick that I used. I used the threading app to essentially run this code on a different thread. And what that does, it allows us to run the Python code on a different thread, therefore not blocking the main thread, which means that this is running essentially in the background so that we have actual animation and we can keep working and modifying the network editor. And then we just say, once we've created the thread and we told it what to run as the thread, just start it. So I'm not going to explain the threading module because it's very complex. You can find it online on this link here. So just check it out. And once again, here is that end result. And that's it. That's the end of this talk. I've shown you a lot of different things that you can do in Python. I've not covered every single thing you can do in Python, but I've kept it to the things that I think most people have benefit of, most TDs that are using Python, people that want to get into Python and Houdini. I've not looked into, for example, generating geometry. I've not looked into rendering or any other sort of complex network creation in, for example, PDG. But this should be a really nice starting point for you to jump off and use to do cool stuff in Houdini with Python with. So with that, I'd like to thank you for your time. And if you have any feedback or other questions about Python, please feel free to reach out to our support at support@sideeffects.com. And with that, thank you and good night.